We're going to put input domain modeling behind us now. We're going to move on into graph coverage. I think most people find graph coverage a little easier to grasp than input domain modeling. All right, so here's our chart of the textbook structure. So here we are in graphs. We're going to kind of talk about all these things to some extent. This week, we're going to be talking about graphs kind of in the more abstract sense. Next week, we're going to be talking about graphs as applied more specifically to source code. The book has sections on applying graphs to design and specs and use cases. I actually have a set of slides that does that, but when we went to the more compressed online format, I've kind of left that out. So the only thing that you'll be looking at, the only thing that you'll be seeing in quizzes or the final exam will be either graphs from an abstract perspective, like we're going to talk about today, or graphs as related to source code. So this is a very, very, probably the most commonly used structure for doing testing. We're going to make a graph model of the thing that we're testing, and we're going to figure out how to cover that graph according to some criterion. Where do we get graphs from? We get graphs from lots of places. The most common place we'll get graphs from is a control flow graph of the software code that we're looking at. Another pretty common case would be looking at a finite state machine. And a finite state machine, I mean, it's awfully easy to derive a graph out of a finite state machine because essentially a finite state machine is a graph to begin with. Typically, and unlike input domain modeling, where we were saying we usually are not relying very much on implementation knowledge, right? So we were considering that to be black box testing. Here, when we're doing graphs, we're deriving graphs from the structure of the thing that we're testing. So this is very, very white box. It's heavily based on the implementation details of the thing that we're testing. So for our purposes, what is a graph? A graph is going to have some set of nodes where that set is not the empty set, right? So it will have at least one node. It will have at least, a valid graph will have at least one initial node where that initial node is part of the graph. It will have at least one final node. And then it will have a set of edges where each edge connects one node to another. And that's just going to be using this, this parenthetical representation here, where node Ni is the predecessor, right? The source. Node Nj is the successor or the destination. So an edge that says Ni Nj is a line, a directed line going from node I to node J. So some example graphs. All right, here's a graph. It's got, well, I didn't write N on here because N is 1, 2, 3, 4. N0, the initial nodes, that's node 1. And so we indicate that initial node with this little unattached lead-in arrow, right? That little unattached lead-in arrow indicates that node 1 is an initial node. And we have a final node, node 4. That has this kind of thicker double border on it that indicates a terminal node or a final node. And then we've got 4 edges. We've got edge 1, 2, which is from node 1 to node 2, edge 1, 3, from 1 to 3, 2, 4, and 3, 4. So there's an example graph. So that meets all of our criteria, right? All of our definition for what a graph is. Now, if we look at this next graph, all right, I've got nodes 1 through 10. I've got some initial nodes, 1, 2, 3. I've got some final nodes, 8, 9, 10. I've got a bunch of edges. Is this a valid graph? Does it meet all the things we talked about on the previous slide?
Yes.
Yeah, it does. It's a valid graph. All right, now we've got another graph we can look at here. We've got 4 nodes, 1, 2, 3, 4. We don't have any initial nodes. We've got a final node. We've got some edges. Well, guess what? Is that a legitimate, valid graph?
No.
No. And why not?
It has no initial.
No initial.
Hi, Professor. I have a question about the middle graph. It
Yeah.
has 3 initial nodes.
Yes.
How do we decide where to start?
So on this graph that has 3 initial nodes, you could, from an abstract perspective, you could start anywhere. Now, from a source code perspective, what does this mean? Well, you know, we've gotten accustomed these days to using modern languages that have single entry points, right? You have a function, that function has one entry point. It might have a lot of returns, so we're accustomed to multiple terminal graphs. We're not so accustomed to multiple initial graphs because we're not used to being able to jump into some arbitrary point in the code. So this doesn't really represent what you would see in a modern piece of software, but it is a valid graph.
Okay, okay. Thank you.
Sure. All right, so then graphs can have paths. And a path through a graph is just a sequence of nodes, right? A sequence of connected nodes, right? So we're going to be traversing edges. And so a few paths in this particular graph, right? 148 is a path. 2596 is a path. 59610 is a path, right? It doesn't have to start anywhere in particular. It doesn't have to end anywhere in particular. A path is just a sequence of connected nodes. And a path has a length. And the length of the path is the number of edges in the path. And I want to emphasize that it's the number of edges, not the number of nodes. So path 148 has 2 edges, so it has a length of 2. A single node, and a single node can be a path, right? It's kind of the degenerate case of a path. It's a path with length 0 because it doesn't go anywhere. And then we can have a subpath. And a subpath is just some subsequence of nodes in some bigger path. So if we look at path 148, then 14 is a subpath of 148, and 48 is a subpath of 148. Then we can have a test path. Now a test path adds another, right? A test path adds another requirement to it. A test path is a path that starts at some initial node and ends at some final node. And a test path represents the execution of some test case. So you can't execute a test case by starting arbitrarily somewhere in the middle of the graph. And you can't execute a test case ending somewhere arbitrarily in the middle of the graph. You have to start at an initial node. You have to end at a final node. Now, any particular graph can have, you know, possibly a large number of test cases. So if we look at this example at the bottom of the page here, which is a single entry, single exit graph, right, having one entry point, or one entry node, one initial node, and one final node. We can have a number of paths through here. Well, specifically, we can have 4 paths through here, right? We can go down across the top, 1, 2, 4, 5, 7. Across the bottom, 1, 3, 4, 6, 7. We can do a crossover from top to bottom, 1, 2, 4, 6, 7, or a crossover from bottom to top, 1, 3, 4, 5, 7. All of those are test paths because they start at an initial node, they end at a final node. Now, it's possible that you might have many test cases. You could have many test cases that execute the same path. You might also have a test path, right, a path on this graph that you might not be able to execute by any test. Not even just a test you haven't written yet, but it may not be possible to execute every one of these test paths. We'll come up with an example to that later. All right, once we've got nodes and we've got edges and we've got paths, then we can talk about making our way down between them. And we can use terms like these. So we can visit. We can visit a node. And so some test path visits a node if that node is in the test path. Okay, that's, you know, pretty straightforward definition. If I've got a test path 1, 2, 4, 5, 7, then that test path visits node 1. and it visits node 2, and it visits node 4, and node 5, and node 7. We can also, our test path can also tour some subpath, right? And a test path tours the subpath if the subpath is part of the test path. So our test path P, 12457, it tours a lot of different subpaths. It tours 1, 2, it tours 2, 4, 4, 5, 5, 7, 1, 2, 4, 2, 4, 5, right? You can see how I'm just kind of going through this. All of the subpaths of length 2, all of the subpaths of length 3, all of the subpaths of length 4, and it tours the entire path of length 5. I could have also said that it tours paths of length 0, right? Because I could say that it tours 1 and 2 and 3 and 4. We normally don't bother listing that degenerate case of, you know, 0 length test path or 0 length subpaths, because usually they're just not that interesting, because it's no better. It's no different and no better than simply visiting the node. All right, so a couple more definitions. Question, can a length of a subpath be 1? Sure, a subpath can be 1. A subpath of length 1, remember that we're measuring the path length by its edges. So a subpath of length 1 has 2 nodes. So here, these first few, 1, 2, that's a subpath of length 1. 2, 4 is length 1, 4, 5 is length 1, 5, 7 is length 1. All right, a couple more definitions. Path with a little t, and again, I'm not going to be like too strict on these definitions and exactly the right representation. So, you know, you don't need to be taking too much in the way of like careful notes. Oh, the small t means this and the big T means this. But the path t, or the path t is the path executed by some test t. And then given some set of tests, big T, then path big T is the set of test paths that are executed by all of those tests. Okay, that's not a very complicated definition. And each test will execute exactly one test path, and that is the complete execution from some initial node to some final node. So let's talk about reaching locations in the graph and reaching them with a test. So given some location in a graph, and a location can be a node or it can be an edge, we can reach that from another location if there's a sequence of edges from the first location to the second. So if I'm at one node and there's some set of paths, or excuse me, some set of edges that I can take to get to some arbitrary other node, then I can reach that node. And we can divide that a little more further. We can divide that a little further and say, well, there's really two kinds of reach, right? I can have syntactic reach, meaning there's some subpath in the graph. I don't care about what the logic is. I only care about the graph structure. I only care about the nodes and the edges. And syntactically on this graph, there's a set of edges I can take to get from here to there. We can also talk about semantic reach, right, where we're bringing in the meaning of the code, right, the meaning of the graph. And now we need to consider for semantic reach the actual implementation logic. Are the if statements or the while statements or whatever is creating the graph, are they written such that I could actually write a test to do that, right? So syntactic reach, we're ignoring the logic. We're just looking at the graph structure. Is there a set of edges that'll take me there? Semantic reach, I also need to consider the logic that the graph represents. And I have to understand that underlying logic to understand whether I could actually write a test to follow that path. All right, so we said early on in the semester that, you know, our basic approach to testing is make some model of the software and then cover that model. So we've talked about making a graph model of software. So now we're going to talk about covering that graph. So we're going to use different kinds of criteria to set up what the test requirements are for our graph. And those test criteria, they're just going to be rules that define what the test requirements are. And so we have two kinds of graph criteria. We can have structural coverage criteria. Structural coverage, this is equivalent to what I just talked about, syntactic, I almost did it wrong, syntactic reach. Structural coverage, we only care about the graph, right? The structure of the graph, the nodes and the edges. And when we're doing structural coverage, we're trying to make sure that the control flow executes successfully throughout the module and throughout the graph. So looking at structural coverage, our first and the simplest structural coverage criterion is node coverage. And that simply requires that every node in the graph be executed, right? That I have a test, that I have a set of tests. And those set of tests are a set of test paths. And those test paths execute or cover or reach, all of these words are equivalent, every node in the graph. Or in terms of test requirements, my set of test requirements for node coverage is the set of nodes in the graph. And I satisfy those test requirements. I satisfy each test requirement by having a test path that reaches that node. So is node coverage the same as statement coverage? Usually this is a good discussion point, but we've actually already talked about this semester. And the answer is, yeah, node coverage is the same as statement coverage, because what is a node? A node is a collection of statements such that when you reach the first statement, you have to execute it all the way through to the last statement, right? So it's a block of statements that don't have any control flow in them. It's just a sequential block. And a sequential block of statements is represented by one node. Then we can have edge coverage. Edge coverage is a little bit stronger than node coverage. In edge coverage, our set of test requirements consists of every edge in the graph. Every reachable edge, every reachable path of length up to 1. Now this length up to 1 thing, that kind of sounds funny. Length up to 1, that means length of 0 is okay. So length up to 1 allows for a graph that have one node and no edges. So imagine that I wrote a function, and this function, I don't know what it does, whatever it may do, but it doesn't have any decisions in it. It's just a set of statements that do some computation, right? That's got one node. It's got no edges. There's no branching. And so we need to define edge coverage as including paths of length 0 to ensure that edge coverage by definition subsumes node coverage. And in practice, edge coverage is different from node coverage only when there's a second edge between two nodes, right? Only when there's some kind of like shortcut. Like here in this example, this is an if-then. I get to node 1, we execute an if statement. If it's true, I go to node 2, I do the then stuff, and then I come out of the statement and I go to node 3. But if I come into node 1 and that if statement is false, then I just jump directly to node 3. So now where for node coverage, I could satisfy this with one test, right? One test path that goes 1, 2, 3. That test path 1, 2, 3 does not satisfy edge coverage because it doesn't satisfy edge 1, 3. So that's where node coverage can be a little more complex and have a few more tests than edge coverage does. Where edge coverage can be more complex and have a few more tests than node coverage does, excuse me. So is edge coverage the same as branch coverage? We talked about this too. The answer is yeah, that's exactly what it is. These edges are representing control flow branches in the software. Well, here's what I just described. What's this with path length up to 1? That seems like a funny thing, and it may seem trivial, and it actually is kind of trivial, but we need the definition to be that way because that forces, that allows us to have edge coverage always subsume node coverage. And that may seem a little obvious in this case, but as we move on to edge pair coverage, I think that case will become a little more interesting. All right, so if we decided it was good to cover all the nodes, and maybe it was even better to cover all the edges, what about covering every pair of edges? And so covering every pair of edges has a really obvious name, edge pair coverage. And so in edge pair coverage, our test requirements to satisfy edge pair coverage, are simply covering every subpath, every reachable subpath of up to length 2. So up to length 2, again, that allows us to have graphs with 2 nodes and 1 edge, or 1 node and 0 edges. So if we look at this graph and we talk about edge pair coverage, all right, where's an edge pair? Well, 1, 3, and 3, 4. That's an edge pair, right? The edge from 1 to 3, and then the edge from 3 to 4. And 1, 3, and 3, 5. That's an edge pair. And 2, 3, and 3, 4. And 2, 3, and 3, 5. And normally when we're talking about edge pairs, rather than writing them as 1, 3, and then 3, 4, we'll just write it as 1, 3, 4. And we understand that to mean the 2 edges between 1 and 3 and 3 and 4. So this suggests an obvious extension. Well, if doing pairs of edges is good, then doing all of the paths, right, the complete path of edges, that would be even better. But we'll quickly discover that becomes impossible if our graph has a loop in it. And so there is a weak compromise to this that basically says, well, we'd like to cover every possible path, but we know we can't cover every possible path because if we have a loop, then it has an infinite number of possible paths. So we'll just let the tester decide, right? Specified path coverage. We'll let the tester decide which ones to do. So let's take a look. I'm going to come back and I'm going to talk about why letting the tester decide isn't a great idea, but let's take a concrete look here first. So if we want to satisfy node coverage in this particular graph, we have to have a test path or test paths that cover every node. So I need to have a path or paths that include 1, 2, 3, 4, 5. Now it turns out I can do that here with one test path. I can go 1, 2, 3, 4, 3, 5. We can follow that down, right? So 1 to 2 to 3 to 4 and back to 3 and to 5. That is a good test path. It starts at an initial node, it ends at a final node, and it covered all the nodes. So I satisfied node coverage in one path. If I want to satisfy edge coverage, what are my test requirements? Well, I have to cover the edge of 1 to 2 and 1 to 3, 2 to 3, 3 to 4, 4 to 3, 3 to 5, right? We can pick out all the edges and list them. That's not too tough. And what is it going to take in paths? Well, this structure here between 1, 2, and 3, this immediately suggests to me that I'm going to need at least 2 paths to cover this. Because if I go 1, 2, 3 as part of a path, I have no way to get back to do 1, 3. So that's pretty clear I'm going to need a second test. But I could satisfy this with 2 tests. We could go 1, 2, 3, 4, 3, 5. That's the same test we ran earlier for node coverage. But I missed an edge. I missed the 1, 3 edge. So now I need another test path to cover 1, 3. And because it has to be a test path, and start on an initial node and end on a final node, it's going to be 1, 3, 5. Now what if I want to cover edge pair coverage? All right, in edge pair coverage, I now have to start looking at all of the pairs of adjacent edges. So I care about 1, 2, 3, and 1, 3, 4, and 2, 3, 4, and 1, 3, 5. I'm not quite in order with what I wrote. My apologies. Interestingly, for edge pair coverage, and this is important, so I'm going to point it out here, and then we'll point it out one or two more times. 3, 4, 3 is an edge pair, right? It's pretty clear that 3, 4, 3 is an edge pair. I go from 3, I go to 4, I come back to 3. That's a pair of edges. But the reverse is also an edge pair requirement, 4, 3, 4. That is a different edge pair than 3, 4, 3, but it is also in my requirements, right? In my list of required edge pairs. So anytime we have these, bidirectionally connected nodes, I want you to start thinking. I want you to think about both directions, and I want you to see that kind of structure and realize, oh, there's an edge pair 3, 4, 3. There's also an edge pair 4, 3, 4. So now I can write some tests, and I'm not going to go through these. I'm not going to read through these individually. But if you follow them through, you can see, yep, we in fact cover all the edges. When I'm doing this on paper, I like to take a little highlighter, right, and say, okay, well, 1, 2, 3, 4, 3, 5. What does that cover? It covers 1, 2, 3. It covers 2, 3, 4. It covers 3, 4, 3. Covers 4, 3, 5. And I'll highlight off the list of edge pairs so that I know what's left that I haven't covered yet. Now, the thing that you can pretty clearly see here, node coverage on this graph took 1 test. Edge coverage on this graph took 2 tests. Edge pair coverage on this graph took 4 tests. It's not necessarily that we're doubling every time. That's coincidental for this graph. But overall, the message here, that as I go up to more strenuous test criterion, from node to edge pair, I'm going to be significantly increasing the number of tests that are required to do the job. And then I have complete path coverage. And if I want complete path coverage, then I've got the path 1, 3, 5, and 1, 2, 3, 5, and 1, 2, 3, 4, 3, 5, and 1, 2, 3, 4, 3, 4, 3, 5, and 1, 2, 3, 4, 3, 4, 3, 4, 3, 5. And we could, of course, go on indefinitely. So I have an infinite, even with this simple graph, I have an infinite number of paths for satisfying complete path coverage. So loops are a problem. How are we going to deal with loops? When a graph contains a loop, we have an infinite number of paths, so complete path coverage is infeasible. Well, this SPC, which was specified path coverage, that's what the S stands for, specified path coverage, that's not very satisfactory, because we decided, under that criterion, we let the tester decide. The problem with that is that then the tests are subjective, and 2 testers might come up with very different tests. And that's, probably bad. At least there's some guidance. It's better than saying, hey, tester, go write whatever test you feel like, right? At least there's some guidance that you're trying to achieve paths. But we'd really like to have a more constrained criterion that forces you to do to write a particular set of test paths, to cover the graph in a particular way, right? Something that's objective and repeatable. And so there are a number of attempts to deal with loops, and these 80s, 90s, and 2000s. These dates are very rough, but there was kind of a maturing thought about loops. And early on it was like, well, we should definitely write a test that executes a loop once. And then it was felt, that might be sufficient. Maybe we should make sure we write tests that execute a loop 0 times and 1 time and more than 1 time. And then in the 2000s, that became a little more, a little more mature. And now we're starting to look at things called prime paths and touring a graph and touring with side trips and touring with detours. And now we have some, some more specific rules that we can use that, again, are objective and don't vary so much with who's doing the testing. So those are what we're going to focus on. So first, let's talk about a simple path. We talked about paths through the graph. We talked about test paths that begin on an initial node and end on a final node. Now we're going to talk about a simple path. And a simple path, you can find the formal definition in the book. I tend to be a not very formal definition guy. So I will tend towards using slightly informal definitions. And a simple path is one in which no node appears more than once, except that the same node can be the first and last node of a path. In other words, a simple path has no loops within it, but the simple path may itself be a loop. So if we look at this graph, 1, 2, 3, 4, and yes, you don't need to tell me that it's not a proper graph because it doesn't have a terminal node. We're ignoring that for now. A simple path is any path through here that doesn't repeat a node, except for possibly the beginning and end. So 1, 2, 1, 3, 2, 4, 3, 4, 4, 1. Those are all simple paths. 1, 2, 4, 1, 3, 4. Those are simple paths. 1, 2, 3, 4, 1. That is a simple path. It is a loop. It starts and ends on the same node. That's okay. What's not a simple path? 1, 2, 4, 1, 3. Right, so 1, 2, 4, 1, 3. Node 1 appears twice, and it's not the first and last. Therefore, 1, 2, 4, 1, 3 is not a simple path. And 1, 2, 4, 1, 2 is not a simple path for the same reason. Node 1 appears twice, not being at the beginning and the end. So then we can have a prime path. And a prime path is a simple path that is not a subpath of any other simple path, which is kind of like, I find that definition to be like, in order to understand recursion, you must first understand recursion. So let me simplify that a little bit. A prime path is a simple path that can't be made any longer. So if I have 1, 2, 4, 1, 2, 4 is a simple path. But 1, 2, 4 is not a prime path because I could go 1, 2, 4, 1, and that would still be a simple path. Now, can I go any longer? No, I can't go any longer because if I try to extend 1, 2, 4, 1 any further, then it is no longer a simple path. So that is my longest possible simple path, which means it's a prime path. So that takes us to prime path coverage. So prime path coverage, this is actually a pretty nice, it's a pretty nice graph criterion. It requires that loops be executed. It requires that loops be skipped. It's repeatable. It's objective. So this is a very attractive. This is a very attractive graph coverage criterion. And it will tour all paths of length 0, length 1, right? It will tour all simple paths up to the maximum length of simple paths. And therefore, it will subsume node coverage and edge coverage. But prime path coverage does not subsume edge pair coverage. For example, you could have an edge to yourself. So you might have a graph like this one, right, where node 2 has an edge to node 3, and it has a node back to edge 2. And that's not that unusual. You could do that with a, with a for loop or a while loop or something like that. It's not an unusual structure. And so if you look at your prime path requirements, your prime path requirements are 1, 2, 3, right? That's the longest simple path I can make. And well, I can't go 1, 2, 2 because 1, 2, 2 isn't a prime path because it's not a simple path because node 2 appears twice. I can catch that edge, by saying my other prime path in here is 2, 2. That's a loop that starts and ends on the same node, so that's legitimate. That's part of my prime path requirements. But edge pair would require 1, 2, 2, and would require 2, 2, 2, or 2, 2, 3, right? So those are edge requirements that edge pair has that prime path does not have. So prime path does not subsume edge pair, and edge pair does not subsume prime path. So let's look at a prime path coverage example. So I can write all my simple paths here, right? I've got 16 simple paths, 1, 2, 1, 3. I can list them all out. And then I basically start to say, all right, well, what are the longest possible ones? Well, 1, 2 is not a prime path. It's a simple path. It's not a prime path because 1, 2, 3 is longer and is also a simple path. 1, 2, 3 isn't a prime path because 1, 2, 3, 5 is longer and is still a simple path. So I basically start throwing away all my simple paths that are subpaths of other simple paths until I end up with this set of 7 that are prime paths because I can't make them any longer. So 1, 3, 4. I can't make 1, 3, 4 any longer and keep it a simple path because to make it longer, I'd have to be 1, 3, 4, 3. And then node 3 appears twice without being at the beginning and the end. 1, 3, 5 I can't make any longer because there's no more nodes in the graph. 4, 3, 4 I can't make any longer because if I go 4, 3, 4, 3, which is the only thing I could do, now node 3 appears. Wow, I was looking at 3, 4, 3. Sorry, 3, 4, 3. I can't make 3, 4, 3 any longer because if I made a 3, 4, 3, 4, then node 3 appears twice, and so does node 4 without being at the beginning and end. And I can't make 3, 4, 3 into 3, 4, 3, 5 because then node 3 appears twice. So I got a question here in the chat. Can we clarify that the prime path is the combinations of those that have maximum lengths in simple path? Yes, that is exactly correct. It is a simple path that can't be made any longer, or it's a simple path that isn't a subpath of any other simple path. Either of those two definitions, which are kind of the same, one is a little more formal than the other. So it's your longest possible simple paths. So what do these suggest? Because there are some interesting cases in here. So 1, 3, 5, this forces a test that loops 0 times. And that could be an interesting case. 1, 3, 4, that forces a test that loops at least once. Because if I take this prime path and I turn it into a test path, that test path has to be 1, 3, 4, and then some other stuff needs to happen and eventually have to come out at 5. So I'm going to execute that loop at least once. 4, 3, 4, that's going to force me to execute the loop at least twice because I have to get from 1 to 3 to 4, that's my first execution, then back to 3, and then back into 4 again, that's my second execution. And I could possibly have a test path that does it more times, but it has to do it at least that many times. So by looking at prime paths, I'm forced to execute the loop 0 times, and I'm forced to execute the loop more than once. Interestingly, I'm not specifically forced to execute the loop exactly once, because I could satisfy 1, 3, 4 by going 1, 3, 4, 3, 4, 3, 4, 3, 4, 3, 5. Right? I could go around multiple times. So that 1, 3, 4, it forces me to execute at least once. It does not force me to execute only once. And there is no other prime path in here that will force me to execute exactly once. All right, we're coming near our breakpoint here, but I want to talk about touring and side trips and detours first. So touring, some test path P tours a subpath of the graph if tours a subpath Q of the graph if Q is a subpath of the test path. The concept is simple. I find these definitions a little bit, they're a little bit wordy or a little bit you know, I guess I'll say a little bit recursive, right? But if I've got, if there's some subpath in this graph, let's say 3, 5, and I have a test path 1, 2, 3, 5, 6, then that test path tours that subpath. So let's tour prime path 1, 2, 3, 5, 6, right? 1, 2, 3, 5, 6 is a prime path on this graph. So let's tour that. How can we tour that? Well, we can tour it directly. We can have a test path that goes 1, 2, 3, 5, 6. That tours it directly. No side trips, no detours. What about touring with a side trip? And we can tour a subpath with a side trip if and only if every edge in the path we're trying to tour is also in our test path and in the same order. In other words, we can side trip to a different node as long as we come back to where we left. So given our prime path 1, 2, 3, 5, 6 that we want to tour, if we toured 1, 2, 3, 4, 3, 5, 6, we have toured 1, 2, 3, 5, 6 with a side trip, right? We captured all of the edges in 1, 2, 3, 5, 6, but with a few extra edges thrown in. A slightly looser version of touring is touring with a detour. In touring with a detour, we're going to tour the path if we have a test path that covers every node as the path we're trying to tour and in the right order. So let me back up here a second and say with a side trip, we were satisfying every edge in the proper order. With a detour, we're satisfying every node in the proper order. So this 1, 2, 3, 4, 5, 6 tours 1, 2, 3, 5, 6 with a detour because we covered every node in 1, 2, 3, 5, 6, but we didn't cover every edge in 1, 2, 3, 5, 6 because we didn't tour edge 3, 5. All right, infeasible tests. We've all gotten to know and love infeasible tests. An infeasible test requirement is one you can't satisfy. How can I have an infeasible test requirement in a graph? Well, I might have an unreachable statement, right? There can be dead code. There can be code that I can't get to. If true, then do this, else if false, then do this, else something else. Okay, I could write a graph, right? I could draw a graph that represents that. But if I've got an if true, else if false, there's no way I can get to the else. I've got unreachable code. I can't actually get to that part of the graph. Or I may have some subpath that can only be executed with some kind of logical contradiction. I need x to be greater than 0 to execute this part of the path, but I need x to be less than 0 to execute that part of the path. And x can't be greater than 0 and less than 0 at the same time. So I can't do that graph. So most test criteria have infeasible test requirements. And the stricter we are, the more infeasible test requirements we have. So if we don't allow side trips or detours, if we insist on directly touring a graph, we're going to have some infeasible, we may have some infeasible paths to tour. If I allow side trips or I allow detours, it weakens my test criteria a little bit, but it may reduce the number of infeasible tests that I have. So this leads us to this concept of best effort touring. And in best effort touring, we're basically trying to do a compromise. We're going to satisfy as many test requirements as we can directly. But if a test requirement is infeasible, then I'm going to try to satisfy it with a side trip. And if I can't satisfy it with a side trip, then I'm going to try to satisfy it with a detour. And if I can't do that, then I'm just going to give up and I'm going to say that path is infeasible. I can't do it. I'm going to delete it from my test requirements. So we're going to try directly, right, and get the best coverage we can. If we can't try it directly, we'll try it with a side trip, or we'll try it with a detour. If we can do that, that's an acceptable outcome. If we can't do either of those, then we'll just decide that that test path is infeasible. Now, the difference in graph coverage from input domain modeling. In input domain modeling, when we found an infeasible test combination, we modified it to try to make it feasible. Here, we're kind of doing the same thing. When we find an infeasible test combination, we're trying to make it feasible by looking at a side trip or by looking at a detour. That's very similar to our, our attempts in input domain modeling to adjust, right, especially in base choice coverage. That's the word I'm looking for, where we're, changing the other characteristics to see if we can turn it into something feasible. That's very much like what a side trip or a detour is doing. Okay, can I weaken it a little bit and turn it into something feasible? And if I can't, if there's no other possibility, then I'll just throw it away. Okay, that was discussing structural coverage of graphs. We can also have data flow coverage of graphs. In data flow coverage, we're going to be looking at not only the nodes and edges, but we're going to be annotating the nodes and edges with variables. And we're going to be looking at where those variables are defined and where those variables are used. And so we might end up with a graph like this. So we've got this this double diamond graph, and we may have a set of defs. So def 1 is x. That means that x is defined in node 1, and def 5 is the set including z. So the variable z is defined in node 5. Then we can have uses. What's used in node 5? Well, x is used in node 5, and x is used in node 6. And so we have all these definitions of variables and uses of variables, and now we can start to look at paths that couple the definition with the value or with the use. So we've got sets of defs. The defs can be referring to nodes, they can be referring to edges. We've got sets of uses that can be referring to nodes or edges. And that just tells us which variables are being defined or used in each case. And then we have a def use pair or a DU pair. And a DU pair is a pair of locations such that some variable is defined at one location, an edge or a node, and is used at some later location, an edge or a node. Now, I said an edge or a node. In fact, a def can only happen in a node, but a use can happen in a node or an edge, and we'll a little bit later see how that's true. Wow, I thought we were closer to break than this. My apologies. All right, so we've got a couple more terms we need to talk about. One is def clear, and what specifically a def clear path. And a def clear path is a path from a def to a use that doesn't have any other defs in it. All right, so if I define a value up here in this node and I use it down here, and I can find a path that goes from the def to the use that doesn't have any other defs of that variable, then that is a def clear path with respect to that variable. Reaching is very similar. If I have a def clear path from some def to some use with respect to some variable, then the def reaches the use. And then we have a DU path. And a DU path is a simple subpath, right? It's a simple path in the graph that is def clear from the def to the use. So these are all kind of related things, right? I defined some value at node up here, and I found a path through the graph that takes me to a use, and there were no other defs of that variable along the way. That's a DU path. So I'm going to back up a slide for just a second and say a DU pair is the def and the use, and the DU path is how I get from the def to the use. And so given a set of DU paths, I can tour those too. right? I can write tests. I can write tests and write test paths that may tour a DU path. And that gives us kind of three obvious data flow criteria that I can look at. I can say, well, I'd like to just make sure that every def ends up with a use somewhere, right? Every time I define a variable, I get to at least some use. Or a slightly stronger one that I want to be able to get for every def, I want to be able to get to every use. Or a slightly stronger one than that, saying I want to tour all possible DU paths. Okay, and that's right. That's what these are. All defs coverage. For every def, I have a path that leads to a use. All uses coverage. For every def, I have a path to all of its uses. And all DU paths coverage. For every def, I have all of the paths to all of the uses. So you can see we're kind of getting more and more constrained, more and more test requirements coming out of these. So let's take a quick look at what these mean here. So if I want to look at all defs for variable x, I need to find a def of x, that's here at node 1, and I need to have a path that leads to some use of x. So 1, 2, 4, 5. That satisfies all defs for x because I go from a def to a use. Now, all uses for x, I have to go from its def to all of its uses. So I need to go 1, 2, or 3, and then 4, and then 5. And to reach the other use as well, 1, and 2, or 3, and 4, and then 6. Those are my test paths, right? My test requirements for all uses. And then we can go up another notch to all DU paths where I need to find all the possible paths from 1 to 5 and all of the possible paths from 1 to 6. And again, just like we saw with edge or with node, edge, and edge pair, we're seeing the same thing here. As I turn up the dial from all defs to all uses to all DU paths, I'm requiring more and more test paths. I have more and more test requirements that it's going to cause me to need more and more test paths to get there. And that gives us our subsumption graph. Yay, subsumption graph. At the top, we've got complete path coverage. Complete path coverage subsumes all other possible path coverages. And that would be great if it was feasible, but because loops make an infinite number, complete path coverage is infeasible. So I can look at subsequent, subsidiary ones to that. I can do prime path coverage, or I can do edge pair coverage. Edge pair coverage will subsume edge and node. Prime path will subsume various others. I think I'm not going to belabor this because we're so late into the night tonight. But again, as you go up higher in this representation to criterion that are more and more subsuming of other ones, they have larger sets of test requirements and will require additional tests to satisfy them. But we'll also probably find additional defects. All right, summary. Graphs, very powerful. We have a lot of different criteria, right? This is good because this lets us do cost-benefit trades. Oh, this thing that I'm testing, the consequence of failure is not very high. I'll just do node coverage. Oh, this other thing that I'm testing, people will die if this doesn't work right. Maybe I should use edge pair or prime path or something that's a stronger criterion that will cause me to write more tests. And graphs appear in a lot of situations in software. Next week, we're going to look at deriving graphs from software. All right, that is it for lecture time. Let's go ahead and break here. I've got 6:24. Let's restart at 6:30 with our exercises.